As you might remember, in the previous video we applied two different algorithms for the same problem and we wanted to compare them. In simple terms, the success of a regression model is how well its predictions match up against actual values. Statisticians have developed error metrics to judge the quality of a model and enable us to compare a regression against another regression with different parameters. Do you remember the example we have seen at the beginning of the regression chapter, where we show the size of the house on the x-axis and the price on the y-axis? Let's focus on it. In this chart, red dots represent the data points and the blue line is the prediction of our linear model. One thing we can do is to measure the difference of each data point to this line. Take the absolute value of each difference and then average it. So we will have a number showing the mean average difference of the data points to our model's prediction. This metric is called mean absolute error. As you can imagine, this method does not penalize the bigger errors and is a bit prone to outliers. If you want to penalize your model more when it does bigger errors, then you can simply take the squares of each differences. As your model squares the differences, it penalizes even a small error, which leads to overestimation of how bad the model is. This technique is called mean squared error, and it is one of the most preferred metrics for regression tasks. In mean squared error, because you squared all the differences, the number you have in hand is a very large number. So in order to make it easier to understand, you can simply take the root square of it. While it's actually pretty much the same thing, statisticians gave a different name for this, which is root mean squared error. Another metric used for evaluating the performance of a regression model is the coefficient of determination, or R-square score. The metric helps us to compare our current model with a constant baseline and tells us how much our model is doing better. The constant baseline is chosen by taking the mean of the data and then drawing a line at the mean. R-square is a scale-free score that implies it doesn't matter whether the values are too large or too small. The R-square will always be less than or equal to 1. To give you more intuition, let's calculate these metrics for our simple model. On this table, you can see the actual price of the house and our model's predicted price for that house. We calculate the absolute difference between these values and total sum of all these differences makes up 170,000. To calculate the mean absolute error, we need to divide this sum to 5 since we have 5 data points. So mean absolute error for our model is 34,000. This means on average, our model makes $34,000 error in its predictions. Cool. Now to calculate the mean squared error, we need to take the square of these differences. Then we average these squared differences and here we get 1.5 billion as our mean squared error. This number is a bit difficult to grasp, so let's take the square root of this value, which gives us the root mean squared error. Calculating the R-square error is a bit different. We have already calculated the mean square for our model. To compare our model with the baseline, we first need to calculate the baseline, which is the simple mean of actual prices. That's $132,000. As in normal, we calculate the mean squared error for the baseline as well. Doing the math, we get an R-square error of 0.44362. So we come back to the starting point. Which of these models applied to a real-world data is better? To compare the two algorithms, we need to calculate these success metrics on the test data, which the algorithms have never seen before. This is a major rule in data science. Evaluation should be done on the data that the algorithm hasn't seen. Thanks to the open source libraries, predicting prices for the test dataset and calculating these success metrics are just a few lines of code. When everything is done, we get the scores for both algorithms as shown in the screen. With lower error scores and a higher R-square score, we have a clear winner. Of course, these results can be improved with additional hyperparameter tuning. I hope all these videos help you get an intuition about regression. Now let's move to the other branch of supervised learning.